Afternoon, everyone. My name is Dale Brosius, the Chief Commercialization Officer for IACMI, and glad that you're here joining us for this version of Innovation Insights for August. Hope you've had a great summer, ready for a very vibrant fall. Just a quick couple of things. IACMI's formed around three major concepts of convene, connect, and catalyze, with a lot of side activities that occur to support those. And for those of you that are members, you already get to experience this. For those of you who are not, please come join IACMI and become part of that. Just a couple of other things. We did have a very vibrant members meeting in June this year, but that's not the only place you see us. You'll see us at various events around the industry each year. A couple of them that I want to highlight that are coming up. Week of Labor Day in Detroit, Novi, suburb of Novi, is the Automotive Composites Conference and Exhibition. It's its, I think it's its 21st or 22nd edition. That is very key to both ground transportation and then urban air mobility is also going to be featured very prominently in this. It's a great show. I know that some of our presenters will be there. A lot of our IACMI members will be there and exhibiting and presenting. So go get signed up for that. Just go look up SPE ACCE and you'll find the link for that. On the back of that, the end of October, we'll be at CAMEX. I know many of you will be as well, in Atlanta. New location for CAMEX this year. And then at the end of November, the week after Thanksgiving, in Salt Lake City for the Composites World Carbon Fiber Conference. So we will be at all of those and hope to see you there. A little bit about Innovation Insights. It's monthly, except for some months when there's a lot of industry activity going on, multiple trade events going on. We said we'll skip it then, or when we have our members meeting, we skip it that. But every other month we do have it. All of those are archived on the IACMI website. So if you go to IACMI.org, you can find that. They're all recorded, so you can get a recording from every one of the previous Innovation Insights going back a couple of years now. So today we've got three great presenters lined up. We have NETZSCH Instruments, Shomerat, and Axle Plastics, all represented today. These are three members of IACMI. Just to remind you that you have to be a member of IACMI to be able to present in these, but you don't have to be a member to attend. So with that, I'm going to stop sharing and I'm going to turn it over to Alec Redmann, who's the Business Development Manager for NETZSCH Instruments North America, and he will give us our first presentation. Hello, just a reminder while Alec is pulling it up, his presentation up, is that if you've got questions, there is a Q&A panel, or you can put it in the chat. Either way, we'll get to those questions in the span of this hour. So Alec, you're all set up to go, and take it away.
Great. Thank you for the introduction, and thank you, Dale and Kim, for inviting me and organizing the event, and happy National Composites Week to everyone. So I'm with NETZSCH Instruments, and I'm going to be talking primarily about our sensXPERT digital mold solution. But as a really quick introduction into the company, NETZSCH North America is located in Boston, Massachusetts. Really focused on thermal analysis, rheology, and measuring like viscoelastic properties. We also have full service testing facilities. And we primarily work with laboratory instrumentation for quality and research and development. And we've kind of transitioned out of that into our new product line with the sensXPERT digital mold, which is really built for in-mold manufacturing solutions. So providing that same laboratory data, but in your process, in your mold. And the quick overview of this is really a three-component of the solution. You have your in-mold sensors, which are dielectric sensors, which measure your material properties. Those are connected to an edge device on the side of the mold, which does all the calculations and computations. So that actually calculates real material properties and gives you that insight into what's happening in the process in real time. And that's connected to our cloud service. So you can actually access this data from any internet connected device, from your phone or laptop, anywhere in the world. You can see what's going on And it also allows us then to implement some machine learning models so we can create some process predictions and optimizations and really help you get in depth into what's happening with your process and what variables could be affecting it. And so a quick overview of what we're actually measuring in dielectric analysis. Some of you are maybe very familiar with it, but it's a powerful measurement technique in that it can see a lot of different material behaviors, viscosity, degree of cure, glass transition temperatures. We combine it with third-party sensors, so pressure transducers and thermocouples. We focus primarily on thermosets, and we can do some thermoplastic measurements. We can measure fiber reinforced materials, composites, even conductive materials, and we range of processes. So injection molding, compression molding, autoclave, really durable sensors that can be placed in the mold. And really what we're measuring is, and what we're looking at is the material behavior under an electric field. So all these molecules have some electric charge. The dielectric sensor applies an electric field to that material, and we see how those ions and dipoles within the electric field shift in that. So it's really an analog to like a mechanical viscosity you would measure in a rheometer. We call it ion viscosity. It's a little more complex than that, but it's nice to simplify it down into a mechanical analog that we can interpret. And the sensors have come a long way. So anyone who's familiar with dielectric analysis in even back in the 80s, you probably had something like this where you had parallel plate electrodes, which is basically just a capacitor with the material in between. We've since been able to transition into an interdigitated comb electrode. So same type of configuration, but like little fingers that are kind of woven in together. And that creates this fringe field and a flat single sensor, which is really nice for in-mold measurements. And this is actually what the sensXPERT in-mold sensor looks like. So that, again, being installed in the mold, measuring the material behavior. And it's really durable, has a ceramic coating, so it's electrically isolated. We don't need any filters. We can actually measure, again, carbon fiber composites or other conductive materials and see exactly what's happening to the material during the manufacturing process. And so if we look at a really quick example, right, standard process data in RTM, resin transfer molding, this is really what you set, right? You have a temperature and a time, and this is what you have. And then once the part's out, then you test it. That's all the data you have, is you just know the time and temperature. Your parts are finished, and then you do some quality control and actually verify that your parts are fully cured or that they're processed correctly. With the dielectric sensors, this is more of what you're getting in the mold. So you can see the viscosity as the material is introduced and actually locates the center. So you can actually track flow fronts. You can see the minimum resin viscosity and look at any effects of aging or any gelation that occurs. You can see the progression of cure, and the inflection point is actually that gel point. And then at 4, you can see that plateau where the completion of cure occurs. So you can track all the way through from the initial viscosity and actually through to degree of cure and the final rigidity of your sample. So this is another really quick video just showing what this looks like in process. Again, the same resin transfer molding. Here we have 2 pressure transducers and a dielectric center in the sensor. The dielectric sensor is that ion viscosity is measured on the top line there. So the top line is dielectric signal. The bottom lines on the 2 lines on the bottom are the pressure transducers. So you can see as the mold fills, the resin comes in contact with the sensor. Here you can see it's dropping down and reaching a minimum viscosity. And really these gates that we put here, these red lines, right, are really just process gates. So you as a process engineer can decide this is what an acceptable part quality looks like, right? All of these, the pressure transducer should follow this pattern. The dielectric sensor should reach this minimum viscosity and start to cure at this time. So we can see all that and track that in real time during the process. And this was really the origin of this whole solution. And then we decided, let's take it one step further. If we have all of this data and we can see if a part is okay or not okay, can we make predictions? So can we early on in the process actually predict what the end result is going to be? And can we make adjustments to make sure that we're not just seeing if the part is okay or not, we can actually control that. And so that comes to really the next step of this, where we implement the machine learning into our edge device. And with our cloud service, we can make constant adjustments to that. And so we start again with dielectric measurements, and we combine the dielectric measurements with the kinetic model, so we have real material understanding. And that's our pre-processing data. So that's the data that we use to really train and test. We create our models, and then we can get predictions and optimizations. And what this looks like is something like this. So continuing with that resin transfer molding example, that pink line is the temperature. That's all we're controlling. We've frozen the time here at 30 minutes. And so we can see that initial prediction of what our process is going to look like at this temperature, right? So we have our target is the dark blue. The predicted measurement at the completion is that green line. And so we can see we're a little slow here in our degree of cure, but we can make that adjustment to the temperature. So as the temperature increases, the prediction updates, and we can make sure that every time, every cycle, we hit that same target. So it's just a really powerful tool. So not only can we measure the material properties live, we can make dynamic adjustments and see what's affecting the process, and just ensure that you have the proper guaranteed results. And so really quickly then what you see, what you actually see, that's all sensor data, but this is what you get as a process engineer and can look online, all of the part data. So tracked by date, by part number, it's all customizable to whatever you want to follow along with. And you can go into this specific part and get really detailed information on the different quality metrics and predictions, and see, really gives you just a new level of transparency and insight into the process. And so if we look at this as a quick case study in aviation industry, we have customers manufacturing really large composite beams, again with an infusion process, but using carbon fiber, and their only real target was a degree of cure greater than 90% before they could demold. And so they had a really long initial cycle time of 760 minutes. And we just installed one of the sensors into the mold and looked at what we could see. And this is like the first 50 parts or so, and we're measuring here the degree of cure. There's these two steps of the process. And this process step one, you can see there's a lot of deviation between the parts in that first 200 minutes. And because there's all that deviation between parts, just because of the size of the part, the mixing ratios, ambient conditions, maybe the temperatures are changing, there's just inherent variation in the process. And so because of that, they needed to have a really long hold time. So that's that second circle from 250 minutes to about 600 minutes. That's just a really long hold time to make sure everything stabilizes. So that ideally we can adjust that. We're kind of doing that same process from I showed before, where we have the temperature is that pink line, and we can make dynamic process optimizations here by just adjusting that temperature. We can increase that degree of cure, make sure it hits the target. And really the end result is we just are able to guarantee a really consistent manufacturing process part by part. Because of that part by part deviation being so much decreased, we can actually reduce that cycle time. So in this case, we were able to reduce the cycle time by 30%, just because we knew we were hitting that target degree of cure in that first process step every time. We didn't need those really long hold times. And so we've had some really good results, again, really focused on scrap reduction and energy savings. The cycle time reductions just come from that improved quality control. And so we're just really helping manufacturing stay up and optimized. So if you have any questions, I guess you can ask them now if we still have a few minutes, or you can just reach out to me. We also have a website specific for this technology that you can visit with sensXPERT.com. Yeah, let me know if I can answer any questions.
So if you've got any questions, you can put them in the Q&A, or you can put them in the chat, and even throughout the rest of the hour. But Alec, we've got one here. Can the system utilize multiple sensors at a time for larger complex parts? Similarly for R&D, can a system combine a mold surface sensor and an embedded sensor in the center of a thicker part, like if you're doing development?
Yeah, so we can absolutely use multiple sensors in the mold. We often do. I think you might be surprised by how few you need, because you can do a lot of calculations and a lot of interpolation between sensors. But we can definitely support multiple sensors, and we can support third-party sensors. So again, we always incorporate pressure transducer data, thermocouple data. All of that can get trained into the machine learning model. I mean, all the data we have helps. Using the something like the disposable sensors, we can do that. It's just becomes more of an issue than in the manufacturing environment. If you're going to do serial production with the disposable sensors, it's going to create some challenges. But on an R&D level, we could absolutely incorporate sensor data from like the thin disposable sensors can go in as well.
Okay. Yeah, because I presume on a thicker part, if you've got a surface sensor, it's a kind of a part averaging thing that's going on. Or is it really around what you can see near the sensor?
That's a great point. So those in-mold, those tool sensors create a fringe field. So you're basically getting like a bulk average measurement through the thickness of the part. They do measure through thickness. You're measuring more than just like the millimeter level. It's roughly, you can measure through the thickness of the part about half the diameter of the sensor. So the larger the sensor you can support, the more through thickness you can measure. But it's like an averaged measurement through that thickness.
So what happens if you've got a 10 millimeter or 12 millimeter thick part? Are you able to see all the way through that?
Yeah, we can see through the thickness, but we can't really slice through and say like at this layer you're measuring this property, right, and at this layer. So to do that you would need to have those the disposable thin IDEX sensors that go in. The tool mounted sensors for bulk measurements, but can still measure through the thickness.
Yeah, and so Rick Power has been my straight man here because I was going to ask you this as well. Is that, I'd seen in the past, and this goes back 10, 15 years ago, dielectric sensors that if you mounted, they needed the surrounding metal to help create the field. Can you do this in an FRP mold? Can you do this in a composite mold?
Yes, we can. I think really, so NETZSCH developed this new tool-mounted ceramic sensor, and that's really what's enabled this to go into production. We know people have been doing dielectric measurements for decades. I think the sensor technology has advanced quite a bit now to where this is a really robust sensor. We can do it in polymer tools, steel tools, aluminum tools. We can measure. It's also much more durable, right? We don't need any like filter papers. Maybe all you need is a little bit of mold release, just how you would treat the tool, and you can integrate this. We're talking tens of thousands of cycles we can measure with the sensor before we see any issues.
Okay. Good. All right. So let's if anybody else has any questions, you can go ahead and put them in the chat, and Alec will tackle those as the hour goes on. And so so we'll move on to our next speaker if you stop sharing. Okay. So we're gonna now go to Chris Mikesell. Chris is the carbon sales manager for Shomerot North America. And Chris, you ready to?
Yep, I think so.
All right, just need to put it into slideshow mode and you'll be good to go.
Can you see my screen?
You can. Just start your slideshow.
Good.
Okay, you're gonna need to go up there where it says display settings at the top. You're no, over to the left. You're still in slideshow mode. I mean, you're not in slideshow. Go put it back in slideshow mode. Or or you're gonna need to switch screens, whatever, but click on slideshow. Okay, now under display settings, you can duplicate slideshow or swap, whichever one you want to do.
There we go. We good?
Not yet. Yep, now we are. You're off and running.
Sorry about that. Thanks, everybody. I'm Chris Mikesell with Shomerot North America. I usually kind of put my head down and make an excuse that we're a French company because of the ballerina, but there is a bit of fashion even to our business where we are today. And I'll go through a brief history of Shomerot and what I want to talk about, which is defined sustainability. So we were founded in 1898 in the Ardèche region of France. Silk weaving was a silk mill was our initial manufacturing process, and it's over the last 125 years, it's expanded to 4 countries. We have 3 sites here in the United States. Mainly, the business unit has changed from silk weaving to composite reinforcements, construction, coatings and films, and garment manufacturing. But there's still a lot of fashion involved in the entire process. About 1,100 employees worldwide. And as a company, Shomura has an edict, you might say, to make the company better for our next generation, and that speaks to a sustainability. They want to make that circle much larger. These are our sites. Again, 3 in South Carolina, 3 in France, a couple down in Tunisia area, and also 1 in China. Here's the original silk weaving operation in the Les Chalards area of France, started by Auguste Shomura back in 1898. Here's the picture of our site. We started in the upstate area of South Carolina at the end of 2014, where I'm kind of responsible. Everybody wants to reduce a carbon footprint, but I think it's in my contract to increase our carbon footprint within the United States. So sometimes I have to argue against that. Little personal journey. When I started in composites 30 years ago in 1993, our largest customer was making these gnomes, Tom Clark gnomes, up in North Carolina. 30 years later, my largest customer is right across the street from that building, making prepregs for this C8 Corvette. And they're also being manufactured right there in North Carolina. Carbon fiber, the original use for it is funny because they took natural fibers like bamboo and cotton and pyrolyzed them to make the filament in a incandescent bulb, and then carbon fiber lost that to tungsten, and for an entire century, carbon fiber wasn't used or thought of very much until 1958, 1960s. So very, very interesting in the way carbon has evolved over time. Here's where we are in the 1960s, taking a pan fiber, making a carbon fiber into the process, and it's kind of how carbon fiber is made today. Our South Carolina footprint, this is the Max 5 machine. Again, we started it in 2014. It's capable of 100-inch wide material. We're able to lay out individual angles, customized angles to let the part dictate where we put the carbon fiber, essentially using less fiber for a certain carbon fiber component. We're also capable of combining fabrics and fibers with the C-ply material we make here in South Carolina. We can make carbon layers on the Max 5 from 50 GSM to 500 GSM, depending on the toe size, and continue to do that today. This was the biggest help we got in manufacturing the C-ply material that we make today. This is Steve Tsai. He's a professor out at Stanford University. He came to our company, I want to say it was 2008, and has evolved his process from 94 years old. He continues to innovate. And the bottom left picture is a picture of him with a double-double meal at In-N-Out Burger. And that is a double-double roll we shared out in the Tacoma area. And he continues to innovate and evolve the carbon fiber process. So at 94 years old, he still says he is learning about carbon fiber and its capabilities and optimizing carbon as you see it today. C-ply by performance. You want a tailored angle to where it gives the user the opportunity again to let the part decide where we're going to put that carbon, so we can angle that carbon to use less of it, to get more performance, to tailor to main and transverse loads. We can adjust our weight in directions. We can adjust the fiber. We can use intermediate modulus fibers, standard modulus fibers, whatever is necessary to make the best part going forward and using the least amount. We also can create complementing angles around these angles that we're laying down. So we could pick one angle and then one other one to maximize our main load and transverse load support. If we don't need fiber in one of the directions, let's talk about taking it out and not using it in that direction. And maybe we put it into a main load direction, or maybe we take it out altogether. These are all considerations when you're designing and making parts. We can go less plies, faster layup, and the ability to just put the fiber where it needs to be. Here's a good example of one of our customers' products. This is a backpack frame. And when he came to us, he was using fabric to make these carbon fiber frames, and he was having good success. When we switched him over to a C-ply configuration, he was even getting better performance, using less fiber and having an overall part cost go down. The one issue that he has to deal with is this company constantly wants to innovate. So even when he reaches an optimization, even when he hits a part that's doing everything he wants it to, he's still got to make some changes to that frame for the next iteration of parts. So every couple of years, he has to make some changes to the design, whether it be performance, aesthetics, or shape, comfort. He has to make those changes regardless of how well the frame might be working for him. Here's the dumb sales guy version of C-ply. Oops, sorry. Dale and I were at the coast a little while back. Excuse me. I don't know why this is now starting. And he lost his bathing suit to a couple of playful dogs. And he said, you know what, Chris? If I had a little bit more fiber in the direction of where those two big dogs were pulling and didn't worry so much about where those little dogs were, I'd probably still have my bathing suit today. And since this slideshow wants to continue on, we will. We'll talk about balance and a quasi-isotropic laminate and how many parts actually need that QI construction. Let the part achieve its own balance within itself and pick your angles to where the part is comfortable where it is to give it a maximum performance. Excuse me. Here's some work we did with the IACMI group several years ago. We took that. Why is that advancing? Sorry. I apologize. I had this working great a short time ago. We took the heavy toe carbon construction and were able to put that toe down to a very, very light weight, stitch that heavy 457K toe to a 120 GSM tape, stitch it together into a 240-gram construction, and make a very, very lightweight construction out of that very heavy toe. And it can serve us quite well in areas of construction, roofing, precast. You have a continuous fiber with a very low cost input. It takes much less energy to carbonize. The heavy toe can be converted into a very thin ply, continuous fibers, shallow angles, and very suitable for large scale constructions. Here's a combination product we did with carbon conversions where we took a recycled carbon fiber mat material. We combined it with C-ply, hoping to take advantage of the recycled material, the conformability of that, and then the very low resin content and continuous fiber of our C-ply. And so combining those materials together, we were able to play around with thermoplastics and thermosets and create kind of a combination product that could be suitable for many applications. Another combination product we've done with Endomax, which is a polyethylene. We were talking about a motorsport application for crash containment. So if we could put this grid structure on the outside of a carbon fiber, in motorsport, we can keep any kind of crash parts from flying everywhere and maybe hurting somebody. That polyethylene has that ballistic property that we may be looking for to complement the lightweight stiffness of the carbon fiber. So so that has some advantages going forward. Here's some new stuff we're working on with Shomura, both playing around with hemp and flax fibers and looking at where we can integrate these products into the market today to tell more of the green story, to use some reusable materials and essentially change of fashion. So here's where hemp and flax at the bottom of your screen kind of stack up against e-glass, and strength to weight ratio, it does look like it'd be a good product to substitute for e-glass in some cases. And we have to have our eyes open to water absorption and the opportunity to integrate these without losing performance in several areas. So that's what Shomura today is working on in France, and where we can either combine these materials with carbon in my case and other glass, any other materials to make the next fashion change in our industry while looking at a more global environmental aspect. Applications in automotive, headliners, trunk trim, different trims. We can make pellet and compounds and thermoplastics with these materials. So a lot of different applications that our company wants to take a hard look at going forward. But we also want to make sure we are going down the right road. We're not just putting our head down and saying, yes, we must produce items with flax and hemp and any other kind of green materials because it's the right thing to do. We will want to make sure it's the right thing to do. So a couple of products with flax. Flax you can use in a continuous filament. So we want to look at a multi-axial reinforcement similar to C-ply, maybe combining carbon and flax into an NCF and stitching it together, and also producing woven tapes and other materials with that flax. Now with the hemp, we would have the opportunity to take that, make a mat and stitch that mat together, either with G-flow type of reinforcement or a Rovacor type of reinforcement, and make that a substitute for the chopped glass that we use today. So that's also something we're looking at. Mats also used in interplies, print blockers. Oftentimes when you're making a thermoset composite, you'll get that bulk ply and it'll kind of print through on body panels and other automotive parts. And if we can use some of these natural materials to keep that from printing through, that'll also be an advantage. Interior trims, surface plies, anything we can make a Class A finish with. And last I want to end with is this is a picture of a bird's nest, which as you can see is about 75% carbon fiber. This picture was taken outside our plant. I could make up the bird story, but they're not talking, and I don't know what actually happened to the birds that were in this nest or how the bird's nest ended up where it was. but it gives a thought. These birds were taking our waste, making their next home, and creating their environment as they go forward with something that could potentially work. Thanks for your time, and I'll take any questions.
Thanks, Chris. Thanks for the shout out about my beach vacation as well. So
Anything for you.
yeah, great presentation as always, and love the innovation that comes out of Shomra. One of the products that you guys make, and I'll call it a bi-X, but it's not a plus minus 45 or plus minus 90. It's it's like a 0 and then just one other angle.
A 0 alpha.
Where some of those become useful.
Yeah, it really, 0 alpha is what we usually call it. Today we produce a 0.45, but we found that when you move those angles closer to each other, they complement each other, and you really lose that tendency for that 0.90 construction to microcrack. So those angles, as you move them closer together, they start to work complementary instead of against. And it really, there's a lot of customers now starting to look into that and how we can create those angles. It'll lay up a lot easier and create a much more robust laminate.
Okay. On the was the flax fiber, which you can do in a continuous format. What's typical aerial weight range you can create there? Understanding, of course, that you've got a much lower density material, so the aerial weight will be lower compared to a glass fiber.
Right, it's much lower. The density of the flax and hemp is about, I believe, 1.4, somewhere in that range. So you can go potentially, probably about, because as you could see, those materials kind of lay up not as nicely as carbon, so probably in the same weight range as a carbon.
Okay.
In a woven type of with more of a mat, you're gonna get a little bit heavier. Sure. But so the thought is to be able to combine those products with the lightweight and stiff carbon, and then an overall density kind of in between the two.
Okay, we got a questions coming from our fan base out there. Any thoughts on making a flow media out of the natural fibers? Somebody says they're not a fan of using polypropylene as a flow media because nothing sticks to it.
Yeah. Yeah. Today we use a lot of veils, and the flow media does seem to work quite well. The flax and hemp today, and it certainly could, and it would flow nicely, but it also takes a lot of resin. And it can increase your part weight just by having a resin content go up higher, where we like to live around 30% resin content. They're much higher than that. So when you're integrating those flax or hemp layers in there, you have to be aware that it is going to suck up a lot of resin. It could affect your surface and also your overall part weight.
Okay, but there may be a reason you might want that too. So surface finish or whatever. Yeah. Okay. And then the last question before we move on, do you recommend any specific pre-treatment, heat or otherwise, before using hemp or flax? And I think it's probably related, to natural moisture absorption. Would you want to dry it out if it comes, as it comes off the roll to you?
That's something you very much need to watch out for, and that's something when we were at JEC, a lot of boat and marine manufacturers saying, "Why am I using this? It absorbs water." So you definitely have to make sure that you're blocking it, you have a moisture barrier, and you have that ability to drive off any moisture content that's in there. And we look at that with nylon 6. You have a lot of the same problems. You have to make sure that you get all that water out of there before you go forward.
Okay, great. Thanks, Chris. You can stop sharing. We'll move on to our final presentation of the hour.
Okay.
Okay, our final presentation is from Scott Waterman, the Business Development Manager for Axle Plastics. He's not with us today, but he recorded his presentation late last week. And Michelle Matschke from Axle will
kick it off for you.
kick it off, load up and do it. And then and Michelle, people can put their questions in the chat. Maybe some of them you can answer at the end. If not, provide your email address and we can get those answered after.
Yes, thank you. If anyone has any questions, they can either drop them into the chat or send them to the IACMI crew, and we'll be able to follow up with them after the fact. But yes, as Dale so well stated, this presentation was pre-recorded by Scott, and I'm really just here push and play. So I can't answer your questions, unfortunately, but we will get you answers for them. So without further ado, let me go ahead and share my screen and kick this off.
Hi, welcome to Axle's webinar, Breakthrough Mold Primer for Advanced Composites. Axle introduces our Extend PRACP Mold Primer in conjunction with IACMI. My name is Scott Waterman. I'm the Global Market Director for Axle Plastics. I've been in composites for over 30 years. I've been with Axle Plastics for almost 20. So now we're going to show you just a quick video highlighting just some of the uses of this new primer. Hi, again, I'm Scott Waterman with Axle Plastics. I'll talk about our new primer, a little interview, introduction. Again, I'm the Global Market Director for Axle Plastics. We're going to talk about why a primer in the first place and the difference between a primer and a sealer, about the product and some of the specifics and the testing we've done, as well as a systems approach for the best possible productivity and lowest cost for using mold release systems for advanced composites. So what is a primer and why would you use it? A primer essentially is a resinous material that seals porosity and acts as a leveling agent for the surface of a substrate. And it can be anything from low density foam tooling boards to fiberboard to high density to metallic surfaces, epoxy molds as well. And there's a benefit in gloss and also increasing the performance for mold sealers and release agents and productivity, which we'll get into a little bit more here. Why did we develop this product? There are other primers on the market, including those from Axle, but we wanted to develop a product that had a quicker cure. Coats can be applied as soon as 5 minutes apart. Higher gloss, easier to get a streak-free gloss surface, and harder, more durable surface, as well as increased performance for the release agents and sealers. So this is an application showing the primer with a wipe on, wipe off, not a buff off, but just wiping off for what we would call a mildly worn, high gloss tooling. So here you can see our lab technician just applying a coat of the PRACP. In this case, when it's a very high gloss tool, really only one coat is probably needed. And then he's lightly, very lightly, just wiping this off, as noted. And you'll see here in the video that a comparison, it won't be night and day differences when the tool is already high gloss, but you can see what it will do is mask scratches and mold marks and allow a better surface for the sealer and the release agent for the tool. Sealers and release agents without primer will enhance mold marks and scratches. The primer will help level the surface, improve the gloss, and make the tool look more consistent. Moving on to some of the testing we've done, and we've done a lot more testing than you'll see in this webinar for most thermoset resin systems, demolding, making molds off of patterns and various substrates, as well as molding parts, everything from hand layup with simple e-glass to carbon reinforcements with higher temp advanced composites resins such as epoxies and cyanate esters. So in the first case, we sealed HDF high density fiberboard with 5 coats on one half and no primer on the other half. And there's a dramatic difference in the release force, over 400 newtons for the side without primer and just 5 for the side with. So here you'll see just a quick application of the primer. The first coat, actually, I believe it's the first coat. And in total, when it goes to release, there's been a total of 5 coats applied to one side. You can see the difference of the finish on the right where the primer's been used. Both sides have 1 coat of sealer and 1 coat of mold release. You can hear the cracking and popping of the part being released without primer. So it makes the release system more effective and helps fill in the porosity. Also for fiber products, it helps block any natural oils or materials that are in there which can contaminate some release systems. Next one we did is a vinyl ester tooled surface. It was sanded down to 120 grit, quite a rough surface to show, and there was a pretty big difference again without the primer as with the PRACP, as you'll see in this quick video. Again, release agent and sealer were applied to both halves of the tool. You'll notice a dramatic difference in the gloss from the left side to the bottom of the screen, which is the right side of that tool. Without the PRACP. And we tested, again, lots of different reinforcements, reinforcement thicknesses, resin types, mold substrates. And although the data could change a little bit in repeating the experiments or doing additional experiments, the ratio or relationship between the benefit of the primer was clear in every experiment. Moving on to the third surface, we treated a carbon fiber mold, sanded to 400 grit. And again, with and without the primer, but the sealer and the release applied to both sides. You're going to see a difference as well. It's hard to see the gloss difference, but you can look at the reflection of the clamp on the left side and see a high gloss, and very little reflection on the right side. Quite an easy first release. Fourth panel we show in this webinar is we did our primer on one side of high density fiberboard and our competitor on the other side, just 2 coats, and then sealer and release were applied the same, 1 coat of each to both sides. And they were both about the same on the first, but as reapplication occurred, the axle primered and release side continued to release, and the competitor's side did not. So here he's actually applying the sealer to the fiberboard. Again, the same sealer and release were used for both sides. The first part, again, very similar. And then the second part, competitive material actually did not demold. It broke the clip, the measured force of over 500 newtons. And normally on a substrate such as high density fiberboard, you would apply more coats of primer and more sealer and release It's done in a lab setting to try to accelerate showing the differences. If we put 5 coats of the primer, 2 to 3 coats of sealer, 5 coats of release, it could take 30 or 40 pieces to sometimes start seeing where one system is letting go or starting to see failure modes where the other one is continuing to go. So Axle believes in what we call a system approach. System approach is using a complete package of properly cleaning the surface, the priming, sealing, an external release, and in many cases, an internal release can also help. And in a separate webinar, we have information showing how the internal releases continue to improve the surface finish, cosmetics, ease of release, flow, and actually enhance paintability and bondability for the molded substrate. So the system approach, in this layman's terms, it's like peanut butter and jelly. The products put together are better than they will be individually. If you just apply a couple coats of primer and go straight to the release agent, you're going to be reapplying a lot more often and spending a lot of money on release. By using the right combination of primer, sealer, and release, you'll actually use a lot less sealer and release and get more parts before reapplication, higher cosmetics, easier and quicker demolds, which increase productivity. The molds will also stay cleaner longer. So sometimes customers are looking from a buyer standpoint of, well, that release costs X amount per gallon, but you're going to use a lot less when the primer is added into the system approach, to the package approach. So you actually can see savings considerably more than the cost of the primer to add it to your system. So some of the processes we've tested the primer in, these are just a few of them, but including RTM light, hand layup, spray up, HPRTM, both PU and epoxy-based systems, as well as up to some hot press molding and press molding where temperature was quite high without any issues or degradation of the primer, sealer, or release system. So we talk about the system approach, and we'll put them out as called simple solutions. So depending on what you're molding, whether you're in polyesters or vinyl esters, and say you're making RTM light, and you want to treat a B side and get much better results and better cosmetics and easier release and less scrap, or you're working with cyanate esters on high temp, high advanced applications, we have a simple solution. Most of the products are the same. There's only a couple changes depending on the resin systems, the substrates. Process also has an impact. If you're working on an automated line versus hand building in individual stations, that can change the type of products that are recommended. But overall, we have a very complete system, including, again, the internal mold releases. The brochures for internals, externals are all online at axleplastics.com and can be found there in PDF form. Just a little bit about Axle. It's been in business since 1941, celebrating our 82nd year, producing mold releases, cleaners, primers, and process aid additives, which is a nice way of saying internal mold release additives, which can provide release, flow, like we said, improved bondability and paintability, because we don't manufacture with sterates or silicones or other materials that would get in the way of physical properties or secondary processes of finishing. Company is still family owned, 3rd generation, and we've been in our state-of-the-art facility in Monroe, Connecticut, going on its 6th year. Again, my name is Scott Waterman with Axle Plastics. I can be reached at swaterman@axleplastics.com. Also on our website, you'll see our trade names. We have a on-site lab where we're heavy into research and development, and our sales team has over 200 years of combined technical experience. My apologies that this had to be a recorded webinar due to a conflict, but I will be certainly available to take calls and answer emails and any questions that might be had after this presentation. Thank you.
Thank you, Michelle. Just a reminder that, that's S. Waterman at axleplastics.com. That's is there a datum if there's a dash in the Axle Plastics, or it's just straight
Nope,
across.
just S Waterman, straight across, just like that.
Actually,
If that's a little too complicated to spell, you can also send the info@axleplastics.com too. I'll get those and we'll make sure they get off to Scott.
okay. All right. Sounds great. Well, we're right here at, and Kim put it in the,
Yes.
put it in the
Thank
chat
you,
here
Kim.
for everybody,
Much appreciated.
info@axleplastics.com. But yes. All right. So, thanks to Scott for pre-recording that and looking out for, making sure we had a full program today. I understand it was an unavoidable conflict that, wasn't there when we signed up for this, but great presentation. I think we had great combination presentations today. We're almost at the top of the hour, and I thank everybody for your attendance, and hope to see you again in September. Thank you.
Thank you, Dale.